So on my laptop, it's now 20 past 4. Welcome to the last, let's say, regular talk, this talk slot today. I'm Peter Sommerlad. I've spoken here before. Just a quick check. Who has never seen a talk by me? Raise your hand. Okay. Then let's tell a little bit. I used to be a professor and then quit my job just before the lockdown. Today I work as a C++ trainer and consultant and do a lot of hobby stuff and every hobby you do with love. And my, let's say, personal lifetime goal is rid the world of bad software. And that's a goal that will take me forward to my grave somewhere, which is hopefully far in the future. I'm a leukemia survivor, so I know how easy it can be that you actually face the end quickly. But I survived, so I'm good now, and therefore I fight after fighting for my health, I fight for better software in the world. And one of the areas I fight for better software is the safety guidelines. Another question, who has used MISRA-C or C++ safety guidelines in their work setting? Okay, a few of you. Some of you might have heard of them. And if you look at the MISRA-C++ guidelines of 2008, when I first looked at them, that's my personal opinion, not official MISRA, it looked like to me like, oh, that's not how I would program in C++, what these rules actually imply. There were several misunderstandings by me, but also the style I perceived the rules, they were written for C programmers trying to program in C++, and the rules were created by Ada programmers, which is not completely wrong, but also not very fair. That was when I first came across MISRA-C++ 2008. And the only thing to improve something is not about complaining, but doing it better. And that's why I joined first AutoSAR and then the MISRA working group on C++ guidelines completely for free. So I didn't make any money out of that. I hope that I can sell some training and consulting afterwards, but that's not the main reason. Main reason is better software. Another thing that I like to share quite often is less code is more software. And that's also why I'm a big fan of C++, because C++ gives me a lot of abilities to abstract things and write less code and achieve more results from the same amount of code, as, for example, I would have to do in C. I have been a C trainer in the 1980s, while still a university student. So I wrote a modular 2 compiler in C as my diploma thesis. So I did significant things in C at the time before, let's say, C++ compilers were usable and available. And one thing I'd like to share as well about C and C++. C was written by created by the world best programmers at the time for themselves. And those of you who have been to this morning's keynote or Jeanette's talk about C, it's trust the programmer. The problem is there are too many programmers, including myself, I wouldn't trust. And if you look at the history of C++, who more or less came from the same group of people, it was written by Bjarne for others to use, not for himself. And that makes a big difference in the philosophy of the language and the abstraction ability. Therefore, even though I know that C has its corner, I still think if you start something new, use C++. Now, where do you require safe C++? Everywhere, safety critical software or systems happen everywhere where, let's say, people might come to harm. And if you consider, okay, I also need security because all those systems today are interconnected. So security is kind of a subset of safety. And now the question is, what makes code actually unsafe? And I should use my clicker, which is a bit more convenient. one big thing is that you might have heard, all of you, is undefined behavior. And there are many reasons for undefined behavior. Some are, let's say, honorable, some are less honorable. But nevertheless, today we have actually compilers and optimizers that make use of undefined behavior and optimize away code that they can prove will have undefined behavior, which is kind of interesting, but also breaking a lot of code that tries to not have undefined behavior, and we've seen examples here today in other talks. There are other areas, if you write safety critical code, it typically tends to live a long time. And that means you have to think about implementation defined behavior because your compiler might actually change or the underlying platform might change. I've consulted projects that switched from an 8-bit processor to a 16-bit processor in their control systems. And that more or less caused them to have to rewrite everything. They did other changes to the surrounding hardware, but more or less they had to rewrite everything from scratch because all those assumptions that they made based on the processor word size and so on were no longer true. And then there's also unspecified behavior. It's where, okay, the C++ standard would give you a reasonable range of potential behaviors that all more or less have the same outcome, but there might be observable behavior from these unspecified areas where you don't know which one is actually happening. And also that might lead to portability issues. Now, what makes code unsafe? The biggest challenge with C++ about unsafe code is actually misunderstandings. We have 2,000 plus pages in the standard, where even those people who work on almost daily basis with these 2,000 pages have a hard time to get their head around about corner cases or interdependencies where page, let's say, 355 says something that is relevant on page 1322, and they are kind of interconnected and together actually specify a specific corner case or a specific feature. That is really hard. So I would claim there is no one single person in the world who has full grasp of what actually is C++. Therefore, we cannot trust those people, so we have to help them. And if you write any kind of code, safety critical or not safety critical, a big thing is have guts. And I don't mean the things that you have in your belly, beyond the cake and whatever you got here, but actually good unit tests. And a quick poll again, who is actually writing unit tests for their code? Whew. I'm happy now. And those who didn't raise their hands, go home and learn how to write good unit tests. I'm not saying that every unit test is great. It takes some kind of learning, but actually having good unit tests is something I'm fighting for more than 25 years now. I've been using C++ unit testing since 1997 for production code. I have not always been a professor or a trainer. And this is not part of MISRA, but if you look at other safety standards like the 61508 or for automotive it's 262, they actually claim you should use current software engineering techniques and processes. And not having unit testing and test automation is not current. And that is something you have to take home. And you have a manager that tells you don't have to write unit tests, we have manual tests. That's not professional. That's not even hobbyish. That's bad practice. Now, if you look for unsafe or vulnerable C++, there are several things where we can actually figure out what's happening. The good things are immediate, undefined, or wrong behavior. That is something I might find either by the compiler with warnings, with a static analysis tool, like doing MISRA checks or other checks, or by having sanitizers in my test environment, or even maybe in maybe not production, but in my test environment, where I figure out, okay, there's something wrong. And the wrong behavior is better something that you figure out with your test automation to see that you get the right behavior of your system. But there are other things where stuff is lurking. Kind of, oh, if I input that number, then my program crashes. That's not good. Especially, or let's say, especially in kind of control systems, you might have a sensor that is broken, and you get a sensor reading that is way out of bounds, but it's just maybe because the plug has corrosion, and that is something you have to work with. And so there might be things that shouldn't happen that will actually happen. So there's data-dependent, undefined, and wrong behavior. And again, there's this evolution style. Software isn't developed and then ready. Today, cars have update functions, which might or might not work well. I did an update to my wife's car, and I'm not happy with the update. But security more or less implies that you have to be able to update. And that means you change the software, and that might actually add to the problematic behavior of your system. And then there's the portability, you have new processors, you have the implementation defined behavior that we already talked about. Now, if we look at MISRA, only few of you have used MISRA. Another question I have, who is using a static analysis tool beyond the compiler warnings in their code or in their build tool system? Okay, there are plenty of those. Now, what is actually MISRA? MISRA comes from the automotive industry, I think in the 25 something plus years. In the 90s, people figured, okay, we have more and more software in our cars, and safety norms ask for, okay, we need some, let's say, process, and better, those processes call for static analysis, and maybe limit the languages to a subset that is kind of safer than the plain language, especially when the language has a standard that says this behavior is undefined, but the compiler is free to accept it. So it's not forbidden to have undefined behavior by the compiler. Now, this started out with MISRA-C in 1998, and there have been successive incarnation of that rule set, and the most recent one was just released for MISRA-C 2023, which is not addressing C23, but I think C17 or maybe even C90. I'm not C99. I'm not sure. I think they have C17 or C11 behind that. MISRA-C++ came out in 2008 for C++ 03, and we have since had a lot of new standards, and now we are about to release, as I said, next on Friday we have the last, let's say, technical changes or let's say technical fixes of problems introduced by editorial work on MISRA-C++ 2023. So it should be released within let's say, within this year. I don't want to promise a date because even though it's not a big process, a lot of work is voluntary work, and there might be some, let's say, final edits, and getting the official PDF produced might have require some signatures by someone that might take some time. And if you look at that, we are addressing C++ 17. Why is that the case? First of all, to know that something is bad behavior very often requires someone who actually made that bad behavior to figure out, okay, this wasn't a good idea. And that's one of the things. Second, there is not yet a single C++ 20 compliant compiler that is fully C++ 20 compliant. And if you want to learn about one feature, go to Danny's talk on modules, where C++ compilers struggle getting the modules feature done. And coroutines was another feature that wasn't ready yet, and we are learning about coroutines here as well, and we're getting there. I'm reluctant to use modules and coroutines at the moment for a safety critical system. Now, what are typical misconceptions? These are things I might have said in the past, and I've heard other people complain about, like MISRA forbids me to write required code. That's not true. Some guidelines are deliberately written in a way that you have to violate them, because we want to make you think about such a violation and have a good reason to do so and document that reason. There is something called a deviation process, and there are rules where we say, okay, you need to do that to write code. But when you do it, encapsulate it, have a single place where you use it that way, and then document that you violated this rule and make sure that you get there. Also, what we're not addressing is this, implementing the standard library requires you to violate a lot of MISRA guidelines, like don't do pointer arithmetic. Well, whoever implements vector is using pointer arithmetic. But that's not actually a problem because you can actually certify that the standard library conforms to a specification, which is actually the standard. And that means you can use it. There's another MISRA rule that says don't violate a function's precondition that you call. That is where you're responsible to actually not violate that MISRA rule. Unfortunately, it's one of those that you cannot check yet. We don't have contracts, so you might not know the preconditions of a function from let's say, a checking tool, but at least we can point the finger to the programmer calling the function like a vector with the wrong index, indexing a vector with the wrong value. And the last on that line is kind of MISRA rules are redundant and conforming and confusing. That is also deliberate. I give a few examples later. But since you can deviate from a rule, there's often a second line of defense that will actually give you a more, let's say, a more stringent rule or a more specific rule. Okay, if you deviate from that rule because you have reasons, this is where you no longer have a reason to violate. Or if you violate this also, you have to have even a more stringent reason to violate that rule. Kind of, okay, you might take cut a corner, but not too sharp. Then you're way out in the abyss. Okay, and also, even if your checker says your code is compliant, doesn't mean that your code is actually doing what you do, what it's supposed to be doing. And I talked a lot about MISRA compliance, gave the example and explained. We have, so compliance doesn't mean you have to have 100% rule adherence, which is actually, in my opinion, unachievable in a real world system. But there's a document explaining the process. And if you want to go there, this is a link to that document. And you find the link also in the handout that I provided in the beginning and I put on social media for you to download. The handout will contain more than just the slides, also the some text explaining what I'm trying to say. We have rules that are those things that can be tool checked most of the time, even though the tool check might not be complete because you easily end up with things that in theory are undecidable, even though you can figure out a lot of situations in practice where a rule is violated, but not having a rule violation cannot guarantee that you're not, by the tool, might not guarantee that you're not violated the rule in your source code. Directives are more kind of things, okay, yeah, we would like you to do that, but there's no means to actually check that with a tool, at least not in a way where it's sensible. There are other things. The tool comes in different levels of kind of mandatory tools. Those are the ones that you cannot deviate. And we have very few mandatory rules. There are required rules that you better not deviate, but in a special case, you can actually deviate. And there are advisory rules that you can actually upgrade to a required rule. But you might also choose a specific advisory rule to actually not be relevant for your project. This should come with reason, but you don't have to actually put a reason for every deviation. Like an example would be, oh, you shouldn't use the names of the built-in integer types because you don't know how many bits those are, so you never know the range. That's a portability thing. If you say, okay, we are working with 32 or more bits processors, we don't care if it is 32 or 64 bits in the future. We don't want to use int 32t everywhere. We just use int. That's fine for a project within reason. You can actually go there. But if you look at those people who had those 16-bit processors, if they now go to ARM with 32-bit, then they might actually have data structures where they talk to outside hardware that is no longer the same size and things are bad. Also, rules are categorized as being decidable or best effort. There are things by theory, those of you who have studied computer science will know about undecidability, and there are easily situations where, in general, it cannot be proven that something went wrong. Now, you could ask, why does MISRA-C++ exist when we have a sequence of MISRA-C that already is there, and there are even people trying to use MISRA-C checkers against C++ code, and they fail to check. And it's true that C and C++ share a lot of vulnerabilities, like pointer arithmetic, whatever. But in C++, often the mitigations are much better. In C++, for example, we can have unique pointers to keep track of our heap allocated memory without forgetting to release it. So no resource leaks, which is kind of a pain in the back to actually get right in a C program. Even if you don't use a static analysis tool, you have resilience mechanisms. Program against the standard and take standard violations as errors. Turn on warnings and maybe even some more, and take warnings as errors. So don't accept code that produces a warning. And if you have a specific situation where you have to deviate a warning or turn off a warning, there are mechanisms to actually tell the compiler, oh yes, I know you would issue a warning here, but please be silent in this specific situation, instead of not turning on the warnings. Because that will actually be present in the source code and will show that there's a reason to actually deactivate the warning. And the biggest feature, I would say, is actually, let me try that, closing parent brace. That's the killer feature of C++ where things get cleaned up. That is something to actually get there. And also use sanitizers and static analysis that you would use. Now let's look at MISRA rules. And I'd like to give you a brief introduction. If you look closely, you see that these have kind of 3 numbers in front, and the numbering is non-consecutive. And the first 2 numbers actually are section numbers from the C++ standard, and if there's a 0, it means there is no corresponding section in the standard, or if the second digit is 0, it's overall for the full chapter of the first digit. And the last digit is just a sequence number where we put the rules in some kind of arbitrary sequence there. We thought about having a better naming scheme, but that is something we just inherited from MISRA-C++ 2008. But all the rule numbers are different today because the standard changed its numbering scheme, except maybe for those in the category 0, but even there the rules have been kind of slightly modernized and adapted. And I also highlighted the keywords shall, should. So shall is actually, again, a required rule. So a function shall not contain unreachable statements. And this is something you might actually deviate from by putting somewhere unreachable in there, or built-in unreachable, to actually be able to tell, okay, yeah, please, dear program, crash if I'm getting here, then my logic is broken, which shouldn't happen, but sometimes a fail stop is a safe way to actually exit a system and have the surrounding hardware or surrounding software actually keeping the system in a safe state in that case. Okay. Some of the rules, like the last one in that list, maybe let's have a look there. It's pointer arithmetic shall not form an invalid pointer. So even though the dereferencing is actually the case causing undefined behavior, but you wouldn't want to have actually a pointer that goes into an area that is completely out of bounds. Now, an example or 2 examples actually for these redundant rules, like an object shall not be accessed outside of its lifetime. which is kind of undefined behavior in C++. But you, except for, let's say, special corner cases, that's one of the things where, I have a writing an operating system, and I know there is something there that I actually need to set some bits there manually in the memory and to get something done. But on the other hand, what might lead to such a situation is returning a reference to a local variable, which is that is verboten. No way to do that. You don't want to return a reference to a local variable. Fortunately, most compilers will actually tell you, okay, that's something you don't want to do. Please treat it as an error. Now, there are C++ specific examples, and I would like to highlight one, because that is actually fixed by the reason for the existence of that rule is actually fixed by C++23. It's the issue with the automatic lifetime extension of an expression in the range 4 statement. So, for example, we have here range 4 statement that calls a make function that returns a string, and then we use a vector of strings, and then with the first element we take the first string and iterate over the characters in that string. And this is error prone, actually immediate dangling if because the lifetime of the actual vector is not extended. So whenever you iterate over the string, the actual string object is already destroyed because the vector is destroyed, which is thanks to Nico, so this is something we have fixed in C++23, but because MISRA addresses C++20, and the actual trick to get around those things is actually we figured, okay, if we limit the amount of function calls that you can actually make right of this colon in the range 4 to one function, then there cannot be an issue with the temporary created, because if that function returns a temporary object, that will automatically be lifetime expanded. And that is the trick to get around that, and the details of the rule tell what is actually counted as a function call. And I forgot to say, if you have a question, interrupt me. There should be a microphone somewhere around. Another example where actually is enums. We learned from Jean-Hét today that, okay, C enums, NVC++, 11 enums, because we can say in C++ what is the underlying type, or for scoped enums, actually the underlying type, even if you don't spell it, is well defined, so you know what the underlying type would be. And there are rules that say, okay, don't use an enum without an underlying type, because that would be an implementation defined type, and C++ would have the same issues as C with that respect. And we even say that unscoped enumerations should not be declared. So you actually see I deviated from that rule by this unscoped thing. So I ignored that I'm not doing unscoped enumerations. And there are other things about enumerations that we actually address. And very often the headline doesn't tell you the details. It's just to get a gist of what the rule is about. And a good tool vendor will actually license the rule text to show to you what you get. And if this, once the MISRA-C++ 2023 is published, it's behind the paywall, but the price for the PDF is kind of in a couple of beers in Norway. It's not really a lot of money. Now, one thing where C++ is distinct from C is its type system. And the only, let's say, the major bad things about C++ type system are those that have been inherited from C and cannot be removed because of backward compatibility. And what is a type system's role? That is something, when you start a beginning programmer, the type system usually gets in your way. You write 4 and multiply it with pi, and then if you have the right language, this will not compile, because the language tells you cannot multiply two numbers of a different domain. One is a real number and the other one an integer. They don't come together. You have to convert either one to actually compute the value. This is the level where the type system tells you to get rid of ridiculous code. If you program in an assembly language, you don't get that support. Whatever you interpret, what's in the register or in memory location, it's up to you how you interpret that. Modern assemblies and processes give you some limitations, but usually it's completely your choice. The precursor of C, the language B, actually had a better syntax than assembly, but more or less its only data structure or only data type was kind of a word, which could be an integer or a pointer. Then came C, which actually gave the world a type system for these kind of low-level programmers with a lot of freedom. So you have casts almost everywhere, and you cast back and forward. And as long as it's not completely ridiculous, either you get an implicit conversion or just a reinterpretation of the data. We still have that in C++, but the MISRA guidelines will tell you not to do that. But the biggest difference is, even in C, you can define your own data types. You can create structs. And the biggest thing we had learned, 90s, that was, was the biggest thing. It wasn't inheritance that was the benefit. It was the first kind of languages where you had the ability to create your own types that were kind of first-class citizens. And C++ is the language where creating your own type, being a first-class citizen, is the most important. That is one of the most important features. It allows you to create abstractions that don't have a performance hit, and work more or less like the built-in types from efficiency and also from the usage, but are distinct, so they wouldn't actually mix arbitrarily. Like if you have an integer for, let's say, counting the revs of your engine, and then you have another integer that, let's say, counts the times you open and close the door to tell you when the hinge must be replaced, and then you somehow compare those integers, that might not make sense, or even multiply them, which might not make sense. But the compiler would happily accept that unless you use so-called strong types to actually implement that. The strong types is something that the MISRA guidelines cannot enforce, but the preamble text actually tells you to use strong types for your domain values and not just ints or doubles or floats or whatever. Now, one little quiz, which I'm not sure I got my answers absolutely correct, but if you have two int values, x and y, what is the probability of you being %, let's say? If it's undefined behavior, it's 100%. If it's kind of 50% or 25% or 99.999%, just get some numbers and shout in or raise your hand and shout in. I will repeat and will tell you what I came up with the calculation. Now let's look at that. X divided by 0. How many percent? 100%. That's the easy part. That's always good to have a question. When you make an exam for your students, the first question must be easy. Just to give them, okay, relax, now you can answer. Now the next question is a little bit more tricky. X divided by y. What is the probability? Assuming, let's say, 32-bit integers. It's nearly 0. How often do you write to check, I don't have division by 0? Those who don't divide by 0, do you also check for min int divided by -1? So it's about 2 cases out of 2 to 32. So it's a very, very low number. I think it's about I'm not sure my computation is correct, but you can write a program to actually check for that, for example. Now, it becomes more interesting. What if you write x plus y? Hmm? 50% was my first assumption as well. Not exactly correct. If it would be just positive numbers, 50% is a good choice. But we have negative numbers as well. And so actually it turns out it's 25%. So probability of having integer overflow with arbitrary integers x plus y, and if you write in a system where you might have bit flips or sensor data that comes in that's wrong, that is something you have to care about. But the even more interesting thing is x times y. Rough guess. Say it again. 90%. Too low. If you would have something where you say, okay, if it's that probable and it would be a good thing, you would bet on it. Don't care. Put $1 million there, I will get it back. It's at least 7 nines probable to have undefined behavior of multiplying to arbitrary integers. It's only the small numbers that work well. So that's actually, I think for 16-bit integers, it's about 5 nines and with, or 4 nines. I wrote a program where I can elaborate all the values, and for the 32-bit, you cannot do that, at least not in a reasonable amount of time that you weren't willing to wait. But I wrote a Monte Carlo system where I checked that, and it's I came up with at least 7 nines. Sean Parent did this computation, and he erred on the wrong side, and I'm not sure if his second guess is more correct than my Monte Carlo simulation. I might have need more runs to actually get there, but it's really a sure thing that multiplying to arbitrary integers getting you undefined behavior. So if you write an optimizer in a compiler, you might actually just replace all multiplication with no code, and because it's undefined behavior anyway. Which is not actually true, but that is something to look out for. And it's easy to get wrong. So built-in types are evil. Signed integer overflow is undefined behavior. Unsigned integer overflow is kind of, the electrical engineers say, oh, that's how this hardware works. I know what to do. Other programmers might not be as familiar with the wrapping around thing and might find it, no, it's not really what we need. And we still have that division by over 0. And with assigned integers, we have also that min-int divided by -1, which is a kind of a problem. And the biggest problem, let's say, in embedded systems, especially with the electrical engineers, they know, okay, unsigned, I wrap around, that's good. And then they use UN16Ts. On a 32-bit machine, and we get integral promotion changing the signs, which is kind of a horror scenario. Especially if you multiply to 16-bit integers, you think that's okay because I wrap around. No, you get signed integer multiplication, and easily you end up with undefined behavior. Now, what can we do about that? I thought long, and people write class types to get that with all the overhead that some compilers provide you with class types. There's one way to get around. Well, we have enumers where you can say what's the underlying type is. And we have, because they form a distinct type, we have kind of operator overloading, and we have concepts to do so. And there's a talk by me at C++ Now, I think 2021 was the talk, remote, where I explained my simple safe integers that first don't promote, and second attempt to be safe with respect to arithmetic by doing all arithmetic in unsigned domain, and then computing the two's complement if necessary. So they wrap around, which is, I'm still have to work on a version that actually detects and maybe does some other things. And in C23, we actually have standardized the underlying mechanics to detect overflow for integer arithmetic. And I might implement it using the built-ins for Clang and GCC to actually go there. And I think there's a version for Visual Studio as well in the library, detecting signed integer or in general integer overflow. And my approach is, unfortunately, we don't see the colors that nicely. So we have UI8 for unsigned integer with 8 bits and so on for the others, plus corresponding operator overloading. And that library is available for free. It has unit tests, and if you find bugs, please submit a unit test to my library. If you really need a commercial version, since I'm the sole author, I'm happy to provide you with the license, whatever you pay for it. Just an example, user-defined literals. In C++20 we can use const eval, so we actually make sure that we don't have any runtime overhead from that, but we have the compile time detection that the literal actually fits the target type that we want to go there. And just to play around, if you want to check with that, that's an example. So there are two lines that are commented out that will actually cause compile errors if you try that. I was too lazy to actually implement some, let's say, having a surrounding infrastructure to detect compile errors from that. Now, okay, integers is one thing, floating point is another, which I don't go to because a lot of embedded systems don't do floating points well. Next problem, types. Okay. There are a lot of MISRA rules. We see these 3-digit rule things about, okay, don't use the built-in types directly. You have to use them to implement other stuff, but nevertheless try to be very conservative about implicit conversions. And one implicit conversion that's forbidden in both directions is to and from bool. Bool has a disadvantage, or some people say it's an advantage, that it's considered an integer. So whenever you have a Boolean value, you can use it to compute something with it. Some people use it for, let's say, interesting multiplications, and multiplying by 0 or 1 is actually okay. That wouldn't overflow. But it's not really, let's say, convenient to understand code that is written like that. And the compiler will actually optimize your ifs to be decent enough to actually not having to do these tricks in your code. Also, character types should only be used for text. That is also philosophy in MISRA. We have these dedicated integer types for 8 bits or whatever, 16 bits, and you might have a wide character type where you don't even know how many bits it's on your target system. And there's another thing, the last line, if you look at the assignment between numbers shall be appropriate. This assignment is capitalized and italicized. You might not see that on the font on my slide, which means it's more than just the equal assignment operator. It's all places where you have a target type that is either fixed or deduced, and you initialize it from another type, like passing an argument to a function, where the function parameter tells you what type you get, and then you pass in a value. If that would require implicit conversion, then that's kind of something where the MISRA checker should actually trigger a warning, or actually an error. Now, there's a lot about casts. So you want to have strong types and you don't want to have casts. Who is using typecasts in your code? Go home, treat each cast that you have to do as a design error. If you have employed the type system properly, you don't do casts. You might construct one value from another. That's the corner case where I allow it. But most other situations where you cast is broken design. There's even broken code, like casting away const or volatile. There's reinterpret cast where you do pointer interesting things. I know sometimes you need to do that, but consider each cast that you have to write in your code a potential design problem. And if you would be my student, which you no longer are, I would ask you to write at least half a page rationale why this cast is actually okay. And then you might think of changing your design. Now for strong types, there are plenty of libraries, also one by me. It's called pst. So if someone tells you, pst, I have something for you, that's my strong type library. It's slightly different from other strong type libraries that you might have heard. I'm not sure. We have Jonathan Müller here, who has a strong type library. We have Björn Fahler here, who has another strong type library, and you have mine. So you have options to choose and to see a little bit how things work. We have that kind of, oops, can we see that there? Oh, I'm always pointing to things that you cannot actually see. So you use inheritance from actually a kind of a CRTP pattern. You say what is the actual wrap type that you wrap, and then you can add in with kind of mix-in classes additional operators like the output operator, relational operators, and here we have additive operators, so you can add and subtract, and that's it, not multiply leaders. And the other version is if you actually want to have more control, you can actually have a member variable and then only mix in the operators, but that would actually get slightly more code to actually write. So it's really not very intrusive and not much code to write to get a distinct type. And it's a little bit more than a type def, but it gives you much more safety because you only get these operators that you actually specify to get. And if you need mixing different strong types in an expression, you might have to write those combining operators yourself, but at least you're sure that you're not getting ridiculous operations. That is the important thing. If you just use a type def or a type alias, you end up with having all the integer or floating point operators at your fingertips, and there's no distinction by the compiler if it's your leader gas type or just a pi that you get from somewhere. There's more on that library, and if you insist, you can actually try it. There's one caveat because it uses inheritance with aggregates. Don't put your types on the heap and then use delete to a base pointer of one of these mixing classes, which you inherit from. That is a corner case, but if you turn that off, you lose the ability to make them aggregates, which gives you all kind of bad properties on some compilers who have who no longer will compile your code as efficient as otherwise, especially on the ABI level. So if you consider all these built-in types that you need to build your good stuff, but not your domain abstractions, use strong types, detect or prevent implicit conversions, prevent signed integer overflow, maybe use a safe numerics library that actually raises exception, like boost safe numerics. And oh, I forgot one thing that we come to, don't use C++ bit fields for mapping hardware because that's non-portable. It's not guaranteed any kind of layout unless your compiler tells you so, and it's implementation defined, so it might change with compiler settings or the next version of the compiler, and don't use bit fields. Now, that's part of class design, and I have more slides on class design. One thing is bit fields and unions, and more or less MISRA says don't use bit fields and don't use unions. And it's not as strong about bit fields as about unions, but at least it tells you a lot about if you have bit fields, yeah, better not have an assigned integer of size 1 because you don't know what actually the true, if it's a bit 1 or 0, if that's -1 or 1 or what it actually means, it doesn't make sense for a single bit field to have assigned type. And for unions, use standard variant unless you actually want to have type punning and bit fields, where type punning more or less doesn't work in C++ as it works in C, even if your compiler tends to tell you, yeah, I'm doing that. It's undefined behavior, even though it works. There are a few corner cases where doing type punning with union are allowed in C++, and I make use of that to actually implement a bit field helper that allows you to specify bit fields with a starting position and a width, and this allows you to actually get there to use a union to map your register to individual pseudo bit field union members where you can actually access them, and the library behind that will actually do all the, let's say, the masking that is kind of the tedious thing to do by hand for you and behind that. And I implement that deliberately because I've seen client code that used a union and also kind of these things, but did it wrongly. They weren't using the mechanism that is not undefined behavior for the underlying punning that is required there. So all these BF things are actually structs with the same member, and between those you can actually individually have different union members active, only one is active, and you can access nevertheless the non-active member without having undefined behavior. That's one of the corner cases where the standard allows it. And I don't have a talk about that bit field type and how it's done, but the code is not that complicated. Now, about class data members, there have been schools of thought telling you, oh, make every data member in the class private. I think that's wrong. Because people tend to make everything private and then have get and set functions for each of the data members, which is kind of ridiculous. Why not make it public? So MISRA and also C++ defines aggregates as having some interesting properties, and it even allows today inheritance with aggregates, even though between, I think, 17, 20, and 23, some kind of corner case wiggling has been done to actually make things safer, where the standard was wrong. But nevertheless, encapsulation is one thing. If you want to change something, it's good to have it encapsulated and not proliferate throughout your code. On the other hand, sometimes it's overrated if it gets in your way of using something. Even though a struct might have just a public data member, it gives you a distinct type that is different from the data member type. And that's a big distinction because it again gives you strong typing. If you use that type as a function parameter, you not easily get a wrong type or let's say a slightly different type be passed down there. Now, my biggest contribution, and I need to hurry up a little bit, is about special member functions. And one thing is if a member function returns some kind of inner parts of an object, you actually should ref qualify that. Who has ever ref qualified a member function beyond example code? Oh, that's a feature introduced in C++ 11. Who has written a function returning a reference to a member function? Those must be ref qualified. Otherwise, you can call them on a temporary object, and that would lead to dangling, immediate dangling. Unfortunately, the standard doesn't follow that. Even this language standard doesn't follow that. And if you go home and analyze that code, you will see where it fails. And actually, ref qualifying an assignment operator would actually help you with that, not having a dangling reference returned from an assignment. There's more about special member functions, and they use that interesting word. Whenever a MISRA guideline gets, if you would spell out what it does, is very lengthy. There's a trick, we use the word appropriately. And then the text defines what appropriately means, which is kind of, okay, we can get the output, limit the output of a tool checker that says, so you violated 1501, and then it will allow you to actually get there. And one thing, we limit the freedom of copy and move member functions. So you wouldn't have a non-const reference parameter for a copy constructor or copy assignment. Remember auto pointer for those of you old enough. Also, we will tell you that if you have a move member function, it must be no except. Otherwise, it doesn't make sense to have a move operation at all. At least for the reason where you want to have move. So these are the signatures for the copy and move operations, and that's more or less the only thing that's allowed for them. And again, notify, we have these ref qualification there and there on the assignment operators, which you unfortunately don't get from the standard defaults, but you will get if you define your own, or will have to do if you define your own, and you should do that actually, regardless if it's MISRA or not. Now, let's look a little bit at that appropriately. One thing that's inappropriate, having a destructor with an empty body. Who has a destructor with an empty body? Ever written one? I have many of those. Go home, when you go home, Friday, delete those. They don't add anything. If it's a virtual destructor in the base class, make it equals default. That's the only change that I'm allowing you to keep it. Otherwise, throw them away. They make your code worse. If you look at the code base of the Mars helicopter thing there on Mars, they have plenty of those. And I said, oh my God, they didn't know C++. Now, there's a consistent definition for copy and move operations. We have the unmovable objects, which are used for scope-based resource management. We have move-only objects like unique manager, and we have copy-enabled object. And we have some other things that are unmovable base classes with virtual member functions. And if you have copy and move enablement, where you do your own copy and move operation definitions, this is only allowed if you have a customized destructor. So one that's not equals default and one that is actually not defined, so compiler provided. Now, unmovable objects have a public virtual destructor and so on. And if you want to learn much more about how those special member functions, watch my talk on what classes we design and how, which would be another 90 minutes talk. And I have some slides here for you for self-study. I distinguish different kinds of types that you would design. Value types, those just work. Relation types that are pointer-like, where you need another object to actually be valid. And when the other object goes away or changes state, that relation type might actually become invalid. And using it means dangling, and dangling is undefined behavior. We have these class hierarchies, which I think are much overused in modern C++ and no longer have that relevance that we thought they have in the 90s, because we were so intrigued by the keyword class that we are able to define our own types. And then came the strange things inheritance that nobody actually understood before we had design patterns, and everybody was using it for everything. It's like when you teach students tool X, the first thing that they do the next time is, oh, we had such a hard time learning X, we use X everywhere, regardless of what that X is. It used to be linked lists or trees. Everybody was implementing linked lists in the first job they had after university. And then we have those manager types. I would actually like to rename them janitorial types, because those are the ones who actually clean up after you're done. That's not a manager job. A manager says, I don't care. Actually, manager makes you not to care, and actually this janitorial types. And let me skip over all these different things, how you create those managers and general managers. And my guideline is take away, use value types, pass by value, return by value. Compilers are very good in optimizing, and there's even obligatory copy elision that you don't, even when you return something, you don't even have to have a supporting copy constructor. Reduce the need for relation types, so everything that's pointer-like. Having a plain pointer, in my opinion, has no standing in any kind of safety critical code unless it's really tightly encapsulated in a manager class. And you never use the plain pointer anywhere else. Unfortunately, we don't have optional references unless you use a non-standard optional, which I recommend at the moment. I'm trying to find the how do you say that, the Don Quixote thing to get optional references. I'm trying to make how do you call that in English? is it a lance? No, or a joust thing? So I want to kind of find the windmills to actually get optional reference in the standard. I'm not sure I succeed, but that's one of those janitorial tasks I like to work to clean up things and use strong types. And I didn't expand on error handling in this talk because now it's just too much to actually tell you, and get rid of this, have guts and get rid of the actual bad things that you might use. MISRA, stay tuned for its release. It's about to be there. I even can use the rule numbers that are the official ones. Those won't change anymore. Nevertheless, even if you don't have a static analysis tool that does MISRA 2023, use your warnings as errors, have sanitizers, and more or less, if you need more training, call me. Oh, and don't forget to check for multiplication overflows. There's a question.
Peter, I'm curious, what is happening after MISRA-C++ 23 is released? Will you continue? Because the last time it took 15 years.
We already have a tracker for issues to actually resolve. And we will address C++20, maybe 23, I'm not sure, because the compilers won't be ready and we might want to have an update before 23 compilers are actually available in the field.
Because many companies in the automotive industry in Germany or in the medical domain still already use C++20. It's already an issue.
I would say the current MISRA rules are, let's say, that's one of the things where you have a directive, use standard C++ 2017, where you can deviate, oh, we are using C++ 20. Mm-hmm. And I think we are good enough to actually have phrased most of the rules because we know what C++ 20 is about in a way that are compatible with C++ 20. But for example, the range 4 thing we had to put in because we couldn't wait for C++ 23 to become standard.
Okay, thanks.
And again, it doesn't stop at MISRA guidelines. If your project has more rules, you actually need to care about safety critical systems, ISO 26262 or 61508, then you must do that. It's not an excuse MISRA doesn't have that rule to create undefined behavior. That was a question. Another one. Take the microphone, please, because I might not be able to hear you.
So you mentioned about bit fields and interfacing with hardware. If you have a sort of, a memory location and a content is coming like from other hardware, like it's the memory transfer from another system, you have some data memory and you want to map it to a known structure. Would that be different from the hardware, or is it done differently, or is it more or less the same?
The code, let's say, C++ bit field types. You cannot guarantee. It might work with the current compiler and you're setting that the bit field actually maps like you intended to map, but there's no guarantee. You might switch a different compiler, it might have a different layout, and it just doesn't work. With my, let's say, if you DIY the bit fiddling or masking or use my library, you can actually, it's standard C++, it guaranteed to work, and it creates exactly the same code as your compiler would do with bit fields, because optimizers are good enough. Did that answer your question? And let's say to have that memory address 4711, where your hardware register is, that is where you write a deviation. So you parameterize your wrapper class that does the operations like blink on or LED on, LED off, let's say the simple example, then you would actually deviate to have in your program the hard mapping to having that reinterpret cast or that address to a pointer to that type, which actually would require to document, okay, my hardware has 4711, that's the address of that register, and you have documented that this reinterpret cast is okay.
It was not really hardware registers, but like if it's a protocol packet of a communication protocol, it's in memory and you have a specification saying like this first means this one. the next.
Again, I recommend to use
Yeah,
something like
okay.
that bitfield
Yeah.
library and not the bitfields of the language, because they are not guaranteed to have the correct layout
Second
across
question:
systems.
Is this likely to work better in normal C, or is it the same in C and C++?
It's the same in C and in C++.
Okay. Thank you.
More questions? I think we are over time. And fun and break is waiting.